This is part of programming. Appropriate pulse generator by which you find its intermediate state, you can store. So the thing is that the same cell, earlier I was able to store 1 bit, but now after effectively utilizing this programming scheme in the same area, eight levels. Is it clear? Okay, so in between eight levels you need to precisely control, and then you can identify the. So it is not like that simply we need to identify. Huh? So we need to then figure out reliability aspect also. Multiple aspects are there. So we'll see. So this is the basic of multi-bit storage. So here another pictorial view graph which you can see here. So as this shape is getting changed, it means it is having a different resistance state in the memory cell, and you can program with respect to voltage and with respect to pulse length. So based on the pulse length, you can see there are different regions are getting. So this colorful region is what? This is the resistance. If you see the blue region means low resistance, as you can see here, this one, and which is red one, this is high resistance. So how it is identified? Based on the electrical pulse. I will show you. So then you will more have understanding on this. So this is kind of a, you can identify appropriate region for multi-level storage. Okay, so this is kind of a scheme by which we can see how multi-level programming will work. So one of the prime region or one of the important thing I would say to get a multi-bit resistance, when we start with any material, so we need to identify resistance contrast. So this is the first thing. If you are doing research or if you are doing anything, so when we start any material, so that material should show a large resistance contrast. If it is showing a large resistance contrast, then we can figure out multi-resistance state. So the first important thing is that you need to identify material and then quickly identify resistance versus temperature, and then you can say that, oh, okay, this is the contrast. See, this is the amorphous region where the resistance is, it is around or more than, I would say, 100 mega ohm. It is, they have reported more than 100 mega ohm. It is huge. And if we talk about this crystalline state, it is in the order of 100 ohm. Okay, so the resistance, if we are able to figure out, then you can later on you can tune, and then you can see that yes, this material is appropriate. And some other property also we need to identify, that speed and power and other thing. So this large resistivity contrast allow multi-bit operation. This is the prime thing. And then crystallization, temperature, and activation energy for better memory switch material. So this is another way by which we can see this. So as you can see, this R versus T, it is very, very important to identify any material to these things. So this is kind of some reported work, and this is a various material that has been tested to get resistance contrast of these material. So as you can see, these are some materials which have been showing the crystallization temperature and all those things. and this compare with other materials. So yes, you can see that this resistance contrast in phase change material, it is much higher side, and it could be applicable for multi-level storage and high density memory application. So this you need to identify. Yeah. So first thing is it is very important. We need to figure out what is the crystallization temperature. This is crystallization temperature and this contrast. So this is various spacing material, as you can see. This is 225, 124, 147, ESD, all. It means you can see that these are the composition. And then later on, it could be identified the potential of this material. So now, after identifying this material property and all, like crystallization temperature and resistance contrast, you should have an appropriate programming technique. Hmm? So programming technique means what? Here you can see this is a typical phase change memory cell, which has been tested for they have fabricated using the fab facility, proper lithography, and then lift off process, okay, and then depositions and top electrode, bottom electrode, appropriate techniques. So I'm not going on to that. So it's a kind of a typical device structure of phase change. Here you can see that this is the narrow channel, and in between this. So this is kind of a circuit aspect of this. And later they have studied some circuit level things. But here I'm focusing on this multi-level scheme. So as you can see, the way you are varying the tail duration. Tail duration means what? So this, if you talk about the pulse, if any pulse. So pulse is having multiple parameters. Okay, rise time, pulse width, fall time. Okay. So if you are having a control on tail duration, okay, so what you can do, you can easily identify the volume of inside the phase change material. As you can see, initially when this duration is less, the material is showing the high resistance, and the state is, you can say, it is more more region you can identify. And the way you are moving towards this higher side of the scale duration, so it is getting crystallized, and this region is getting shrinked. Okay, so what happened? Actually, you are controlling the heat inside the memory cell. Okay, everything is depend upon the voltage which you are providing, and based on that you can see this. Okay, so this is the experimental result by which we can see that after varying the electrical pulse parameter, we can easily tune the state of amorphous volume. So this you can see that the amorphous phase, how it is getting changed, and then we can tune, and we can identify the multi-level. And then in between, as you can see, these are the, if you are able to tune here, so you can get different state. If you are able to tune here, you can get different state. Similarly in this case. So as you are moving, you can get this. Is it clear, all of you? Okay. Another scheme is that where again they have varied the falling edge. Falling edge, as you can see, this is the falling edge. This is the falling edge. This is the falling edge. Is it clear? So here they have given a long falling edge. Long falling edge. So as you can see, when you have given longer duration, so material is very close to crystalline state, as you can see. Okay, and when you have suddenly removed this, so it is not getting proper crystalline. Okay, so this is as simple as you have heated up and you have slowly you have cooling down. This one, as you can see, you have heated at particular point, and slowly you are removing your voltage or your programming pulse. Slowly you are removing, as you can see. So the way you are removing slowly, so material is getting more time, and it is getting ordered. Okay, and here, as you can see, you have removed, so it is not getting much crystallized. So this is the way by which you can easily identify appropriate programming technique. Okay, so by which we can see. And similarly, on another approach of this pulse duration, they have a staircase way. In a staircase way, they are tuning the multiple resistance state. Okay, they have heated up and then reached into one state, and then again they have reached to one state. Is it clear, all of you? So pulse scheme is very, very important if we want to identify a multi-level storage. So we need to very carefully understand about the pulse. If you are able to identify appropriate electrical pulse, then you can easily tune your state. So if do we have marker? Okay. Just I will show here one basic understanding about. So if here, as you can see here, this both diagram, it is fully depend upon your pulse. So we need to figure out when we talk about voltage or current. So it is not simply it is simple voltage you are providing 1 volt, 2 volt, 3 volt. Okay, it is fine. When we talk about RF or pulse based measurement, in that case we need to figure out these things very. So as you can see, this is your time. This is your time, okay, and this is your voltage, okay. So your voltage, it should be the parameter. It should be like this, like this, like this, and this. Okay. So this is a typical pulse where you have a rise time and you have a fall time, and this is your pulse. Correct. And what you can do when you program any memory cell, this kind of a memory cell, which we can see here, this one. This is the memory cell. So what they can do using appropriate pulse generator, you should provide a voltage like this. Okay, and having a control on this pulse parameter along with amplitude. Okay, so not only amplitude of any pulse is responsible. Okay, if you have given a single 1 volt and for longer time duration, it means time you have increased, then also you can change the state, and same 1 volt time has been reduced, then also. Only thing is that you are having a control on these parameters. Okay. So one case, as here they have shown this figure, as you can see. So here what they are doing, they have a control on this parameter. Fall time. So fall time means what? They have given a constant pulse like this, then like this, like this. So what will happen? Here you are providing a longer time. Okay. You have reached that particular level, and slowly you are removing the bias, and then you can tune the state. Is it clear, all of you? So in this way, the pulse programming is very, very essential to identify a different amorphous volume to tune the state of any PCM cell. And as you can see, this is the multiple levels starting from level 1, level 2. So these are the different levels. See, it is getting to settle at one level and then different levels. So these are the different levels by which we can tune the memory to identify a stable multi-level operation. Okay. And if we see the another way, so another way is called partial reset program. Partial reset means what happens? Here you are in the reset state, and you are just providing a systematic increasing amplitude of voltage, as you can see here, this one. Okay, and based on that, you are identifying. So here, what we were doing earlier, here you are having first control on pulse duration. Okay, first case where you have seen the pulse duration, where you are having a control on pulse duration, not amplitude. On another case, which is I am showing, this is pulse amplitude, amplitude, pulse amplitude. Is it clear? Okay. So initially you have given some different pulse. As you can see, they have reached at particular level and they have set. So first you have set the device. Set the device means resistance is very low. Resistance is very low. You have set the device, and then after that, systematically you have increased the voltage with some kind of step size. Step size means what? You have just given fixed. Pulse parameter is fixed. Okay? TR, TF, TW. This is fixed. This is fixed. Okay? And then you have systematically increased in this way. So this is called as a control on pulse amplitude. Pulse amplitude, and then you are figuring out the different state. As you can see, the way you are increasing the amplitude, the resistance is also getting increased, and you can tune this resistance to identify multi-level resistance. Is it clear to all of you? So this is the just brief idea. Okay, this is just brief idea how we can do that. But yeah, we need to figure out lots of things. Calibration is required. You need to provide appropriate electrical pulse, voltage pulse. Then only you can understand this. So these are some kind of way how which this resistance is getting changed. And these are some kind of probability statics of 4 different levels. It should be proper distinct. Then only you can identify these reasons. It is well identified. And this is some kind of reliability issues, as we can see here. It could be seen these different resistance level, but this red state, as you can see, it is getting varied. So this red one, it is belongs to the resistance of amorphous state. So it is reported that there is kind of a resistance drift. Drift can be identified. So drift can be, you have stored at one particular resistance state, and later on, due to drift, that atom gets settled down in a different manner, and the resistance state gets changed. So this phenomena, it is oftenly it is seen in the case of amorphous phase, and it could be, this is the important research problem. It could be seen. People can identify a material which has very less drift. Okay, so this can be identified a good research area where we can identify a novel material based on the phase material, where there should be a minimum resistance drift so that we can both levels should not get mixed. Is it clear, all of you? Okay. Now, here in this particular work, as I told you that first you need to identify a material, and then you need to get that state of this. So this material, which is long back, it is reported IST material. It has, it was showing this multi-resistance state, and that I have studied earlier. So it could be, it has reported in 1988 for optical applications. The important thing is that here it is showing the multi-resistance state, as we can see here. And the crystallization temperature is also very huge. So it could be a thermally stable material also. So we have done some kind of a study on this to identify this multi-resistance state. To the way I have discussed the basics to you. So in this line, I have explored this material. So initially, we have figured out the resistance contrast of this material. Okay. So yes, the resistance contrast is pretty much high. In this case, as you can see, this contrast is bit higher side compared to other reported material like GST 225 and GT material. And yes, we have. It is also showing some kind of a crystallization at 300 degrees Celsius, and then it is getting crystallization, and then finally at 400 degrees Celsius, it is fully crystallized material that could be identified. So this is the one step where we can see that yes, it can be helpful. And then we have tried to figure out this material to identify whether it can be shown for multi-resistance state or not. So we have done some kind of this multi-resistor. We have annealed and then we have cooled down, and then for subsequently we have checked this. So this material is getting settled down at one particular state. So the resistance, which is higher side, and then also upon annealing, the resistance state is getting settled down at particular position. So along with that, with higher crystallization temperature, it could be identified. It could be seen that yes, we can further explore for device application or some electrical characterization, multi-level application. So to see this material. So multi-level storage in this material, it could be important to see the property of high-level storage. So what is the reason behind getting this crystallization, and then subsequently at higher temperature it is getting more crystallized? So we have figured out using high temperature XRD measurement of this material. So we have seen around 300 degrees Celsius, where this 300 degrees Celsius, this one, as you can see. So at 300 degrees Celsius, what happens? So at 300 degrees Celsius, there is a kind of a binary phase formation we have seen, indium antimony kind of, and then subsequently at 400 degrees Celsius, 312 phase has emerges, which is the more stable phase for memory application, and then subsequently it is growing. So this is the confirmation what happens electrically. So this we have tested. So further, the crystallized orientation of this 312 phase, this is more or less material side to identify how this material works. So where orientation of this material is also calculated using this texture coefficient of this XRD data. So it has seen that this 312 peak of 200, it is getting oriented the way we are increasing the temperature. So yes, it is a more stable material. So to get the main R point, to identify multi resistance state or multi data storage of this material, what we have done, we have discussed, we have given this kind of electrical pulse. This, as you can see, this is using source meter, and we have systematically increased this value to identify this material for multi-level operation. So how it could be done, as you can see, prior to electrical switching, the way we are increasing the current, so this is a sub-threshold conduction, no switching. Huh? So from 0.7 microamp to 3 microampere, so this is what? This is short of your amplitude of current pulse. Okay. So at 3 microampere there was no switching, but the moment we have given 7 microampere, you can see there is a sharp change. Sharp change means what? There is a material got switched from one state to another state. Okay. And then subsequently, when you were increased further up to 28 microampere, it was in the particular intermediate resistance state. And then subsequently at 32 microampere, again we can see the final. So it can be seen that yes, this material can be helpful to explore for multi-level storage. So after having a control on current, so as you can see, current controls set operation. So what we are doing, we are stabilizing the material, and then we are looking into these multi-resistance state where it could be identified. So how? So just I will brief you about because in this case you need to identify the material, first material, and then you need to tune the state. So you need to understand the equipment part, how you can do that. So in this case, if I talk about, so here, just I will draw here the pulse scheme in this, because for multi-level storage you should have a pulse scheme appropriately. So here you have this kind of pulse, which is having amplitude I1, okay, this one, and then this is I2, okay, and then subsequently you have increased this one. this is I3. Okay, I3, I2, and then I1, and so on, In in this way. Okay, so this is the magnitude by which we are enhancing from 0.7 microampere to 32 microampere systematically from here to here. And each state, this is rising and this is falling, constant. Okay, so it's a kind of a DC measurement for having a control on that. So as you can see here, the way we are increasing, so we are getting a proper current change by which we can identify a multi-resistance state. Okay, so this is the way by which we can see this, the change in the voltage inside the cell. Now, further, if we figure out more closely on this state, so these states are distinct. 8 state it could be identified: S1, S2, S3, S4, and S2. It means 8 distinct level can be seen in this material. But I'm not telling that it could be properly seen earlier also, because this is in case of set. Further reset operation we need to identify. But this is in case of set operation, we have seen systematically it is showing the 8 distinct level. 8 distinct level means how many bits? 3 bits. Okay. So this is the way. This is the way by which we can see this. Huh? So this is the way 8 different levels it could be seen. It is easily distinguished. And so this is actually this region, this picture which you can see that this is the close view of this region, this one. Okay, where the read has been done, very small region. Okay, so as you can see, then further for proper distinction of these levels, the way you have increased the current, we can see here how is each resistance level it could be different. Okay, the way this is x-axis is your applied current and this is resistance. It could be seen that initially it was high and then suddenly drop and then systematically drop, and you can tune this. You can tune easily these materials. So this IST is compared with GST and doped SBT. So you know what is the important thing in this case? The on and off ratio, it is reported in this case, it is higher side. It is around 570. 570 means from here to R highest and R lowest, it is higher side. So if it is higher side, means yes, we can use this material for further application and we can test it for multi-level applications. And if you see, it is reported for same programming scheme for GST, it is around it is 148, and for doped SBT, this is at 7.2. So in both cases, it is much higher side. And this is the colorful contour graph by which we can see the programming region, systematic programming region with respect to different current value. So how the resistance you can identify. So initially, as you can see, this is partial set operation. So initially, it is very high resistance state, and the moment you are increasing your current pulse, so it is getting down towards steady state. And as we can see here, in between we are getting intermediate resistance state, which will be helpful to identify this. So as this scheme, it could be helpful to further identify multi-level operation and multi-level storage of this material. And another interesting property of this thing is that along with multi-level storage, you should also have kind of high speed also. As in earlier I have shown that along with multi-level storage, your material also it should high speed transition also. If we are able to get high speed transition, so we have given a first to identify this threshold voltage. So this is just to see whether the material is in which what voltage it is getting to switch. So it is around 1.9 voltage. So here just what I wanted to show you, the switching actually. So the switching for this reported material, this is in this particular work, it is around 300 picosecond. This is the fastest reported value for this. So earlier you can see this device is fully in off state, and the moment this 1.9 voltage it has been provided, So after a delay time of around, you can say this value, it is got switched, and systematically this value is getting decayed. So yes, this material, it could be also seen for high speed operation and device application, which is fasted. It could be seen, has been identified for fasted at around 300 picoseconds. And the fast set operation, the way we have seen set multi-level operation during set operation. So how it could be for ultra fast switching. So this 1.5 nanosecond of pulse width of this uh, voltage, which is having a 1 nanosecond of rise time, 1.5 nanosecond of pulse width. So we have seen here the shortest delay time, which is matches with earlier reported things, around 300 picosecond, when the material is switched from amorphous high resistance amorphous to fully steady state. The time duration, it is around 500 picosecond. It is very less as compared to earlier reported value. But yeah, it is comparable with well-known material. But yeah, here interesting aspect is that yes, you are getting a large resistance contrast, which could be easily comparable. So now this is the way by which we can see the potential of this material for multi-level storage, and how we can see in further to enhance the data capacity. And this fast set operation along with the lowest one, how if we are increasing this value from 1.5 nanosecond to 5 nanosecond, as it could be seen that. So you can see it is from off to on. This current is increasing. Current is increasing means the device resistance is getting reduced. That's why you are able to see that current. If you are not able to see the current, it means device is not set. Okay. So that's why, as you can see, the way we are increasing, it is getting increased and then getting down. But the interesting aspect is that at 3 nanosecond, as you can see, the current has increased. It is got settled down at particular intermediate state. If we will see, you can have a more study on that, because we have not done any in situ characterization on that. What happened exactly here? So it could be seen that, and then after that again it is getting increased that current value, and then it is getting settled down. So it could be have we can see what's happening inside this material into that fast time scale, fast voltage pulse, and it is changing the current. So for multi-level, you can also vary the pulse width. The way I have discussed few minutes back, having a constant amplitude but just varying the pulse duration, also you can change the current. So this happens actually. This is the best example. So what happened here? We are giving a constant voltage of around 2.2 volt or something, 2.5 volt. But you can see in each case the current is changing. Okay, current is changing. Why? Because you are increasing the time. You are increasing the time. That's why it is happening. Okay, so you pulse duration and pulse amplitude both are very very important if we want to figure out multi-level storage, and then you can tune that ST. So this is the analysis with respect to that. So this is the conclusion with respect to that, which we can understood about the multi-level operation, where we have seen uh, the pulse duration based and pulse amplitude, how we can see these material, and what is the pulse scheme, what is the multi-level storage kind of mechanism, how we can do that by having a control on pulse duration, by having a control on pulse magnitude. And then we have explored some material in phase change material, basically INSBT, and which has shown crystallization temperature as 300 degrees Celsius, having 8 stable multi-resistance state, and then large resistance ratio of 570 and ultra high speed operation. So yes, we can say that yes, it is having a potential candidate for a high speed and multi-level storage. So yes, with this, just I will stop here, and yes, I can take questions from the audience. Yep. Can you give me a water?
slide, let's see, like you talked about the crystal orientation. So does the crystal orientation affect the PCF performance?
Uh-huh. Yes, actually, sometimes crystal orientation means if I talk about this material here, we 312 crystal is having stable configuration, okay, and some other like 225. So if you have that desired crystal, if you are getting, it is getting oriented with respect to temperature, then you will get a stable memory. Okay, if I want some one particular crystal and upon increasing temperature that is getting down and another one increasing, then it is not stable. Some phase segregation is happening, some kind of thing is happening. So in that case, so it is very important what you are targeting. So it should be oriented, then only we can say that yeah, this is stable. Yes. That is also that I told you. If you see that Thailand, this multiple materials are there: germanium, antimony, tellurium, and some doped sb2t. Or so the specific composition. So people have studied a specific composition of one element, and then they studied, okay, this property is that, and then they have varied that property. So based on that property, you are getting some specific desired property like melting temperature, okay, and the kind of switching speed also. I mean, there are multiple things by which you are getting a stable. So that composition also matters actually. So if you are doing more on material aspect, so they need to figure out the stable composition, okay, on which you are getting a stable switching. Stable switching is very important. Stable matlab, what is the meaning of stable? Stable means if you have fixed your memory at logic 1, so it for a long time it should be holding that time. If it is not stable, after some time you will everything will finish. So composition is matter, so you need to figure out this.
So in the RT measurement plot, you mentioned about the heating rate. It was 5 degrees Celsius per minute. So how did you come up with that number?
Mhm. I mean, you are telling that how I got 5 degrees Celsius.
Yeah. And how will that affect the transition?
Yeah, so first thing is that how I got this heating rate. So for heating rate, you need to first calibrate your heating uh, element by which you are heating your sample, and then you need to figure out the heating rate. First of all, you need to provide the time, up to what time you want to reach from lowest to highest temperature. Based on that, you can identify the heating rate. Slow heating means slow heating rate, okay. And if I have given 10 degrees Celsius fast heating, but the thing is that during fast heating you will get overshoot. If I want 400 degrees Celsius at 10 degrees Celsius, it won't. It may go at 430, 440. So one thing is that. So with that, how I figure out? Say suppose I'm doing heating on furnace. I can show you in my lab also. We have a heating element on which we are heating that. So in PID controller, you can fix this issue to get the heating rate. First thing. Another question is what? Your next question?
How did you come up with that number? Like, what happens if it would be 10 degrees Celsius per minute and 3 degrees Celsius?
Yeah, so we have done few study on that. As you can see that the number which I have shown you. Just so with fast heating, what I have observed here, the crystallization temperature is getting increased. So this I observed actually, but I need to identify exact thing behind that. Okay, I mean the way if we are doing a slow heating, so you what you will get? You will get a less crystallization temperature. It means material is getting a it is taking some time. Okay, but in case of highest, you are getting, so it means crystallization temperature it is varying. Okay, so in that number, so just I have tested this material for different heating rate, and then we can see that. So what I could see that if you provide a moderate heating means where the 5 degrees Celsius per minute I am telling you this number. So with multiple tests in is this particular heating rate, I got a stable transition from amorphous to crystalline. Okay, so that's why I got this number. Okay, anything else? Yes.
Hello, sir.
Hmm.
Currently, we don't have a pulse measurement in our lab, but we do the voltage that sweep. So in that sweeping, what does this current mode and voltage mode like differs?
Uh-huh. So what you are doing? You are doing.
Doing the sweeping only. Basically, we are doing the voltage sweep
Mhm.
or the current sweep.
Uh-huh.
So I found it for my material, like I'm able to see the same kind of graph that you were having.
Uh-huh.
So for my in my case, like I'm finding it when I'm doing it with the current sweep, but
Okay.
through the voltage I'm not able to figure it out actually.
Okay. Okay. So in both case, you need to in current control, when you having a control on current, you can easily see this. Why? Because normally when we talk about current, so 1 nanoampere, 1 microampere, 1 milliampere, in that way, if I'm varying, so I can see the change. But in case of voltage, possibly in my, what I'm thinking, what you are doing, I think you are just providing sweep means just 0 to 5 volt. And what is the step size you are taking? Step size, it is zero point 0.1 volt or zero point 0.5 volt, because sweeping means you should have a appropriate step size.
So we are having a step of nearly 101, like 100 steps. So in current mode, from I used to usually set the current from 0 to 5, like
0
that.
to 5.
Yeah.
Okay, okay. And with 100 data points in
Yeah,
between.
with 100 data points in between, something like that.
Okay, okay. So in that case, what I can suggest, if you want this multi-level, so then you can identify with current, but with voltage control having this DC sweep, you should have a precise control on voltage, like 100 millivolt of step if you provide, in my opinion. If you provide a very less, around zero point 0.1 or even lower, 0.05 volt, then only you can easily see, because voltage should be slowly it should increase. In general, what we are doing, just we are taking 100 data points, and in which way it is arranged, that we cannot identify. So we need to systematically increase this voltage. So you have to identify about that your instrument, and then only you can figure out.
And so one more thing is why we are applying a triangular pulse, because like theoretically when we were discussing, a lot of times like it was like a square kind of.
Square.
So but then it's like basically like I've seen when I went for some characterization for my IV, they are giving a pulse like how you were saying,
Yes,
like this,
yes,
and
yes,
then it will
yes,
go.
yes,
So
yes.
why
See,
we are.
this study, it is focused on current control set operation, first of all. So you cannot provide current with your pulse generator, first of all. Am I correct? As of now, with your pulse generator, you can source a voltage. That too, if pulse means, what is the meaning of pulse? Pulse, when you go for high speed characterization. Okay. So when you go for high speed characterization, then in that case you need to source voltage only. High. Have you seen any pulse generator which can source 5 nanosecond of current pulse? It can. That's why here I have given a triangular pulse which is having a large time. Actually, time is very high side. So, but if I want to target a study on pulse, then I cannot. So that's why I have given a triangular pulse. So it is a triangular, but it is more or less DC analysis only. It is not just here we are figuring what is the minimum current to switch, minimum current. Okay. So this is the way. So pulse characterization means when we figure out a high speed transition, है ना? We need to check a high speed, and then we need for more programming aspect, more in which way. And this kind of a study, it could be identified what is the minimum amount of current. So it is, yeah, we can see that it is in the order of microamp, very less. That too for bigger device. We have not developed these devices for appropriate lithography and very small contact size. If you do in that way, then you can reduce that also. Okay. Yep. Anything else?
So just a brief about tail duration, sir.
Uh-huh, uh-huh.
So just a brief about that.
So tail duration means it's a kind of you can say the duration of the falling edge which we are telling that. Okay, so they are referring as this tail duration. It's a kind of a nomenclature which they are using. So it is more or less the okay. Anything else? So multi-level storage is one of the important aspect for increasing the density. Increasing the density. If you want to increase the density of any memory, so this is very important. And this programming aspect, it could be also explore in further direction if you want to enhance the density. So this is more or less towards in this direction. Okay. So I'll stop here, and further if you have any doubts, so yeah, I will be available here. You can go through the content. You can see whatever you have. You can think about this. If you got any point, feel free to discuss with me. Okay. 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 Thank you. Thank you then.